The floor is yours.
Okay, thank you for the invitation to speak. So I'd like to begin with some background and motivation for considering the homology of Eilenberg-MacLane spaces. So as we might recall, Eilenberg-MacLane spaces are these very classical objects where we have a KGN, where G is a group and N is a number, and these have the property that their homotopy is concentrated in a single degree. So we have that pi star of, I'll abbreviate this as Kn, of this Eilenberg-MacLane space is going to be G if star is equal to N and 0 otherwise. And these spaces have the property that they represent ordinary cohomology. So if we're looking at the cohomology of some space X, this is going to be equivalent to the homotopy classes of maps from X. So I guess here I should specify the coefficients. Into K G star. So these spaces have very, very simple homotopy, but computing their homology is much more challenging. So in the 1950s, Serre applied the Borel theorem to the path space vibration, which goes from the loops. So at this point, we're going to, our group G here is going to be Z mod 2. So the loops on Kn plus 1, which is equivalent to Kn, mapping to the paths on Kn plus 1, which is contractible, mapping to Kn plus 1. And this was used to compute the cohomology of Kn plus 1 given the cohomology of Kn. So this Borel theorem is a spectral sequence sort of theorem, which says that if you have a simple system of transgressive generators in the cohomology of your fiber, the cohomology of Kn plus 1 is going to be polynomial on the transgression of those generators. So this is all very classical work, but this talk is supposed to be focused on equivariant homotopy theory or computations in that. So we want to be talking about the equivariant setting. So in the equivariant setting, we have various analogues to classical objects. So in this table on the left-hand side, we have a bunch of very classical objects. We have the simplest sort of space being a point, G equivariantly or C2 equivariantly, where C2 is the cyclic group of order 2. We want our points to have the possibility of having some sort of group action. So we consider the orbits C2 mod C2 and C2 mod E as our points in the setting. And if the analog to F2 being a group is to consider the C2 constant Mackey functor F2, which is an algebraic object which keeps track of coefficients at these two sorts of points. And then if we think back to the geometric motivation for homology, a homology theory is something, or ordinary homology looks for holes in your space. So we have n spheres, but we'd like them to have a group action. So we let V be a representation of our group. So for C2, the cyclic group of order 2, V is going to either be the one-dimensional sign representation or the one-dimensional trivial representation. And SV is taken by forming the one-point compactification of this representation. So specifically, this gives us a C2 action on our spheres. And corresponding to classical Eilenberg-MacLane spaces, we also have equivariant Eilenberg-MacLane spaces, where now these correspond to a Mackey functor along with some representation. And then another difference is that in classical non-equivariant story, the homology of a point is concentrated in a single dimension. In order to have a suspension theorem for our representation spheres, we need to grade on a larger set, which is where this ROC2 grading is coming from. So here, the grading is over the real irreducible representations of C2. And the homology of a point in this setting turns out to be much more complicated. It's something that's infinite dimensional. We'll see a bit more detail what that is later on. But the point of this is to say that in this equivariant setting, we have a bi-grading on our Eilenberg-MacLane spaces. And so given either the homology or the cohomology of some space KV, we want to compute both the cohomology of KV plus 1 and so I guess this should be equivariant, which is usually denoted with a 5-point star. And we also want to compute the cohomology of KV plus sigma. So the new piece is proceeding inductively in the sign representation direction. And this is a setting in which the Borel theorem doesn't apply, so it's useful to consider some other tools. And the tools we're going to be considering come from the study of Hopf rings in homotopy theory. So first, let's recall what a Hopf ring is. In this setting, the Hopf rings are going to be graded. So we'll say that a Hopf ring is an object in the category of graded co-unital, co-associative, co-commutative coalgebras. So that means our Hopf ring is going to consist of some sequence of abelian groups, denoted n sub I, and each of these abelian groups will have a coproduct, and there will be a graded multiplication here denoted with the circle product. And one place that Hopf rings arise in homotopy theory is in the study of omega spectra. So
wait, Serre?
Yes.
I am still digesting the definition. Can you go back to the previous slide?
Absolutely.
Yeah, so the multiplication, because here we just have a graded co-associative coalgebra. Where do we get a multiplication from?
So, let's see. It's from it being a ring object.
Oh, so is there a nice monoidal structure and it's a monoid in that category? Or let's see.
So
because we certainly don't expect the multiplication to have all those nice adjectives, right?
right.
Yeah.
Yes, so the multiplication is not like it doesn't have to, it's not necessarily commutative, it's not,
Right.
yeah, it just has some sort of multiplication that you
Okay.
write down. So yes, monoid structure.
But yeah, I want to say that it should be some monoid in there, right? Does that sound legit or?
Yes, that does. So the multiplication should distribute over addition, so you should have that property. But
So are you, Martin, you're just saying the word monoidal maybe like is a monoidal object in the category? Is that what you're suggesting?
Well, yeah, I want it to be a monoid in some monoidal structure on that category of graded co-unital, co-associative, co-commutative, co-algebras. I just want to make sure that that's correct, that I'm not just being too optimistic here. Okay, but yeah, yeah, maybe I'll just look at the explicit structure and we'll roll with it.
okay, all right.
Thanks.
Yep. So in this setting, we're considering an omega spectrum G. So this is a sequence of spaces together with structure maps between them. And since G is an omega spectrum, it's going to represent a generalized cohomology theory, with the cohomology of a space X being equivalent to the homotopy classes of maps from X into the spaces of the spectrum. And since the cohomology will have the structure of an abelian group, in the homotopy category, the spaces GK will also have an abelian structure. And in fact, since they're infinite loop spaces, they also have the structure of an H space. So this H space structure will denote with a star. And if we apply a multiplicative homology theory with a Kuhn isomorphism, then this gives us a star product in homology, and it gives the E homology of the spaces G, the structure of a Hopf algebra. So at this point, we already have a lot of structure on the homology, but we can ask for even more. We can suppose that G is a ring spectrum, then the cohomology will have the structure of a graded ring, and this has a corresponding multiplication on the spaces of the spectrum. And on applying E homology, we get a product here denoted with the circle product, making the E homology of G into a Hopf ring. So an idea pursued by Ravenel-Wilson was that one could create many elements in homology from just a few, starting with somewhat known homology and then taking all the star and circle products to construct additional elements. And they successfully applied this idea to compute the mod P homology of classical Eilenberg-MacLane spaces, the Hopf ring for complex cobordism, and the Moravec theory of Eilenberg-MacLane spaces. So as motivation for the equivariant computation, we'll first focus on the classical mod P homology computation. So we can consider the Eilenberg-MacLane spectrum for FP, and the spaces of the spectrum are Eilenberg-MacLane spaces. And up to homotopy, HFP is characterized by the cohomology of a space X being equivalent to the homotopy classes of maps from X into Kn. So we have a star product on our spaces Kn. HFP is a ring spectrum, so we also have a circle product, and ordinary homology with field coefficients has a Kuhn isomorphism. So for these reasons, the homology of all the Eilenberg-MacLane spaces forms a Hopf ring. So we have a lot of structure, but we'd really want to know which Hopf ring is this.
And sorry, Sarah, can you remind me what the co-multiplication was doing in that setup?
So the co-multiplication is giving you, well, it's part of, the co-multiplication is part of like the Hopf ring structure that you need that at each of the levels. Does that answer your question?
Yeah, I'm wondering in that topological situation where we're looking at the homology of some omega
Yes.
spectrum, where did we get the co-multiplication from?
So the
Let's see.
co-multiplication is also from having a Kunith isomorphism. Having a Kunith isomorphism for your spaces is going to guarantee that the homology is in fact a co-algebra. Without that, the condition wouldn't necessarily be satisfied. So if you don't have a Kunith isomorphism, yeah, you wouldn't necessarily have a Hopf.
I see. So you just
even.
Right. So you apply the Kunith isomorphism just to the diagonal in spaces, right?
Yeah.
Okay.
Yes, exactly.
Thank you.
To the diagonal spaces.
Perfect.
Yeah. Okay. So Ravenel-Wilson used a number of tools to actually compute this. One of them is the bar construction. So this bar construction comes from taking a quotient of a product of n simplices with points in a topological monoid A. And one model for this is to think of the points in the simplex as giving coordinates along an interval. And then the space is topologized. So the coordinates in our simplex are coming from, we think of them having labels in the monoid A. So give that labels. And the space is topologized so that if 2 points in the simplex come together and collide, you multiply the labels. And if one falls off to the boundary, then the label is identified with the identity in your monoid. And this explicit sort of model is useful because it also gives a very explicit way to describe the star product. Namely, if we have some other point in this space, the star product is given by simply overlaying the two intervals. So this won't be exactly to scale, but roughly you'd overlay the intervals and then the labels would all come along as well. And this space, this construction is useful because it is a de-looping functor, meaning that if we apply B to some Kn, this will construct be Kn plus 1. So we have a way to inductively construct these spaces, but we're really interested in homology. So a useful tool for computing homology is a spectral
wait,
sequence.
sorry, can you go back to the previous slide? Something funny
Yes.
happened with the order, and I'm not sure what exactly happened with the order.
Oh, so here, here you're taking this interval and laying it on top of this one. So maybe the drawing wasn't so clear exactly, but you're just laying them on top of each other.
Okay.
And then yes, the labels.
Okay, you just superimpose everything.
Superimpose everything.
Take all the symbols that appear.
Exactly.
Okay.
And then if anything's on top of each other, multiply the labels.
Got it. Thank you.
Yep. Okay. So this construction can be filtered by taking the portions just up to a T simplex with T copies of A. And this has associated graded pieces, which are T spheres matched with T copies of A. And if we apply homology to these filtered spaces, we get the E1 page of a spectral sequence computing the homology of BA. And one of the nice properties of this spectral sequence is that the E2 page has a very nice description in terms of Tor. So if we're computing this for our Eilenberg-MacLane spaces, Km, we take Tor over the homology for the E2 page, and then you have the rest of the spectral sequence to compute, but then this will converge to the homology of the Km+1 space. So some useful things to recall is that the homology of K1, so at the prime 2, K1 is RP infinity, and at odd primes, it's a lens space. This is exterior on a class in degree 1, tensored with a divided power algebra on a class which I'll call alpha parentheses 0 in degree 2. And if we're working with FP coefficients, this is going to be equivalent to taking a tensor product of truncated polynomial algebras on some classes called gamma p to the I of alpha parentheses 0. So this truncated polynomial algebra is defined by taking fp adjoint x mod x to the p, and these classes, it's kind of a lengthy name, so we will call these alpha parentheses I. So we're starting with, in the homology of K1, something that's exterior and truncated polynomial, and using homological algebra, it's not a terribly difficult exercise to compute that Tor over an exterior algebra is divided power on the homology suspension of x. So this E1 is raising the degree of x by 1. And Tor over a truncated polynomial algebra is exterior on the homology suspension, tensored with divided power on the transpotence.
And sorry, Sarah,
Yes.
is the notation there for gamma the same gamma as in divided power operations, the usual gammas? Or is that just a coincidence of notation? Because in
I think, let's see. So I believe they should be the same, I believe, because it's you're rewriting your divided power that's on one specific class in terms of a bunch of.
yeah,
So I think
let's
they're
see.
the same.
Right. I mean, the usual gamma sub n, I think, isn't that the one that wants to of x that wants to be x to the n over n factorial? And if we were
Right.
working with rational coefficients, if I remember correctly,
Yeah.
that's what it is. And do those satisfy those kinds of relations? Let's see. Or there's some relation along those lines. Maybe it's off by some
Right,
factors.
some indexing or something, but something that could definitely be easily worked out, maybe after the talk.
Yeah, okay,
Yeah.
but okay. It was so the uppercase gamma is definitely the usual notion of divided
Yes.
power algebra.
Yes,
Okay.
this is exactly the usual notion where it's like these sorts of that sort of structure on the algebra. Yes. Yep.
Thank you.
Okay, so this allows you to at least get to the E2 page of the bar spectral sequence. But there's some structure we haven't used yet. We haven't used the circle product structure. And the circle product structure, this is induced by some map from Km and Kl to Km plus L, since this is coming from the cup product in cohomology. So this circle product can be described very explicitly and constructed inductively on M. So if we want to construct it inductively, I should probably give you the base case. And the base case go from K0 crossed with KL to KL. And K0 is simply FP. So we'll have Q circled with some point in KL is going to go to that point, star product with itself Q times. So that's how we'll define the base case. And then to inductively assume that the circle product on M and L has been defined, and then replace both Km plus 1 and Km plus L plus 1 with their bar constructions, which is what we have in the second displayed equation. And then we'll define this map by keeping the point that's in the simplex the same and taking the circle product in Km and KL, which is something we already know how to do inductively. And what Ravenel and Wilson show is that this construction is both well-defined and does in fact give the specific pairing, product pairing that they were hoping to achieve. So what's useful about this is it gives a very explicit description that Thomason and Wilson are then able to show that the circle product in fact factors through the bar construction. And this allows you to inductively describe the circle product on the associated graded pieces inductively as well. And this leads to a pairing in the bar spectral sequence. So compatible with the circle product in homology. So here we just have like an ordinary circle product in homology from the homology of a Km plus 1 and KL to Km plus L plus 1. So compatible with this circle product is a pairing in the bar spectral sequence. So if we have the bar spectral sequence that will be converging to this homology in the bar spectral sequence that would be converging here. On the ER page, there's going to be some circle product pairing, and at the E1 page, the circle product pairing is given very explicitly in terms of the iterated reduced coproduct. So the strategy is we want to compute something over here. So we're going to identify it in terms of circle products of elements in homology that we already know. So Ravenel and Wilson, an example of doing this would be we'd start with the homology of K1 and compute the E2 page. So this exterior term on E1 is going to give rise to a divided power class on the E2 page, and this truncated polynomial is going to give rise to both an exterior part and a divided power part when we compute the Tor term. And then we identify circle products. So we identify these terms on the E2 page in terms of circle products, and this allows us to say that once we identify them in terms of circle products, the circle product of two things has to be a permanent cycle. And it turns out to be the case that you can identify all elements on the E2 page in terms of circle products. These gamma p to the i's, these are coming from applying B to S1, which is K Z2, otherwise known as CP infinity, and this has a map into K FP2. So there are, in this specific example, there's some additional elements that we have to identify, but for all of the rest of them, no additional elements show up, and you can identify everything on the E2 page in terms of circle products. So this means that we can inductively deduce the homology of Eilenberg-MacLane spaces using standard homological algebra.
Sarah?
Yes.
About that conclusion that I'm trying to fit different pieces of a story together. When I think homology of Eilenberg-MacLane spaces, I think of the classic work of Cartan and collaborators, and
Yes.
it's quite involved. And now I'm wondering, what's the precise relationship with the Hopf-Ring methods of Ravenel and Wilson? Is the Hopf-Ring approach giving you an alternate approach to the same computation, or is it ultimately streamlined, more convenient repackaging of the same calculation?
So the exact relation is something that Dev Sinha and I and several other collaborators are currently thinking about. In terms, we'd like to be able to describe this very explicitly geometrically, hopefully. But this method is a bit different from the basis that you get using the Cartan method. The Cartan is like iterated bar construction, which is similar but different in that you're using the bar spectral sequence and this pairing and circle product structure. So somehow you get a very different sort of like your cycles look different, have a different appearance using the circle product. So the direct relation between the two is not immediately obvious.
Nice. So it's, not only a genuinely different method, but even reading off the answer is different, right? They're expressed in different ways.
Yes, exactly.
But just for fun, if we spell out the first few actual abelian groups, or in this case F2 vector spaces, we do get the same answers, right? Or
right. Oh yes, okay. They are the same answers. They do agree.
But just written differently.
Is this giving the homology of Eilenberg-MacLane spaces, but with some extra structure, I guess, that you don't maybe have that you don't see in when you like this traditional computing the cohomology of Eilenberg-MacLane spaces?
Yes, because here you get like the Hopf-Ring structure, which you don't have from other methods.
Right. Okay, thank you.
Yeah. So explicitly, once Ravenel-Wilson do this computation for all the spaces at the prime P, the answer they get ends up being in terms of generators in the homology of K1, which are these E1s and alpha parentheses i's, and classes coming from CP infinity, and they need some indexing sets to keep track of which circle products to take. But with the right bookkeeping in place, they're able to show that the homology is exterior on circle products of E1 with alpha i's and beta i's, tensored with a truncated polynomial part on alpha i's and betas.
Sorry, also, is this computing the homology of all Eilenberg-MacLane spaces at the same time?
Yes, it is. Well, it's at least written down that way. If you want to know the homology of a particular space, you can tease that out by which degrees things need to be in. But yes, It is all of them at once.
Thanks.
And then at the prime 2, this can be written entirely in terms of circle products of the homology of K1. So I've included that here mostly as a remark because we'll see some mirroring of this sort of different ways to write the answer in the equivariant case as well. So at this point, are there any other questions before we move on to the equivariant computation? All right. So to remind ourselves of the ROG graded setting, most generally in the ROG setting, G can be a compact Lie group. We've mentioned that V is a real representation of our group, and we form spheres by taking the 1-point compactification of that, and our homology theory is going to be graded on the additive group underlying the real representation ring for G. So in this talk, our group is going to be finite. It will be the cyclic group of order 2. This has 2 irreducible representations, the one-dimensional trivial representation and the sign representation. And taking the 1-point compactification of those 2 leads to the 1 sphere and S sigma, which is S1 with a conjugate flipping action. And here we have some pictures of, so I mentioned that the homology of a point in the setting is an infinite dimensional non-Noetherian ring. And these pictures show where copies of F2 show up in different representation degrees. So in my picture, the topological degree is along the horizontal axis. So for any representation, C2 representation, we can write it as Q copies of the trivial representation and P minus Q copies of the trivial representation. And then the number of sign representations is along the vertical axis. So each of these integer lattice points in the 2 cones is a copy of F2. And this picture on the right is just a more succinct representation of that. So we also have an Eilenberg-MacLane spectrum for the C2 constant Mackey functor F2 up to C2 equivariant homotopy. HF2 is characterized by the cohomology of a space X being equivalent to the homotopy classes of maps from X into KV. So we once again have a star product on the spaces KV. HF2 is a genuine equivariant ring spectrum, so there's a notion of the circle product. So we can at least consider these 2 things and see if we can compute with that. So since we want to be able to proceed inductively in both the sign and trivial representation direction, we need a way to build B sigma KV, which will be KV plus sigma. And the twisted bar construction does this. And the twisted bar construction is very similar to the classical one, just with the addition of a C2 action. So if we have some point in our bar construction, and gamma is the non-trivial element of C2, this is going to act on the point in our space by flipping the coordinates. So T1 will be sent to negative T1 and T2 to negative T2, and then gamma will also act on the labels. So this can be very explicitly described, and the star product can be defined similar to in the classical case as well. This also gives rise to a spectral sequence. We can filter the twisted bar construction. This will now have more complicated associated graded pieces where we get a representation sphere smashed with T copies of A. But we can still apply ROC2 graded homology to this and get a spectral sequence computing the homology of the twisted bar construction on A. So we can look at computing this in a particular example. So in this example, we'll compute the homology of B sigma of K0. K0 is F2. This space I usually denote as K sigma, but it is sometimes called twisted RP infinity. So it's the space of lines through an infinite number of copies of the regular representation. And The E1 page of the spectral sequence is going to be the homology of this representation sphere smashed with the copy of some number of copies of the homology of F2 t times. And when we put, so in drawing this spectral sequence, the gradings in this picture are still the representation gradings. So the number of sign representations is on our vertical axis, and the topological degree is on our horizontal axis. So the filtration degree is hidden. But when we look at filtration degree 0, we get a copy of the homology of a point in degree 0. In filtration degree 1, we get a copy of the homology of a point in degree sigma. In filtration degree 2, we get a copy in degree rho, and so on. So this has this repeating sort of pattern where it goes, there's like 2 of these copies at one height and then shifts up 1.
Sorry.
Yes.
In that notation, what was the homology of F2?
So this is, so this should really be reduced homology. So F2 is going to have the same homology as like S0 in this ending. So it's the reduced homology of the 0 sphere.
Okay, thanks.
So that's how we're getting a copy of the homology of a point at each of these different gradings. And we can notice that in this particular case, the filtration degree, which here is 0, 1, and 2, and so on, matches the topological degree, which is the degree along the horizontal axis. And a DR differential can only shift the topological degree down by 1. So in particular, it can only reach backwards that far. And we have this whole nice gap in here, which means that there can be no non-zero differentials for r greater than 1. So this leaves the possible case where we could maybe have a D1 differential, which might look like this, in which case it would hit this entire cone. But if it hit this cone, double cone, it would get rid of all of the homology in a given topological degree. And we know the homology of RP infinity has a generator in every degree. So, and equivariant homology always restricts down to the non-equivariant answer on the underlying level. So we would contradict a known computation if we had a D1 differential, so there can be no non-zero D1 differentials. So this gives the homology of twisted RP infinity. I'm going to name some of these classes. The class in degree sigma we'll call E sigma. The class in degree rho we'll call alpha bar parentheses 0. And this should remind us notationally of the homology of RP infinity. If one does a little bit more work, you can deduce that the homology of K sigma is in fact exterior on these generators, E sigma and alpha bar parentheses I. You can also compute their coproduct. Their coproduct is a bit more complicated than in the non-equivariant case. Specifically, you have terms where these elements A and U in the homology of a point show up. So that's one thing that's different. There are some other examples in which the twisted bar spectral sequence does collapse. So we we did the homology of RP, if twisted RP infinity, it also collapses for twisted CP infinity, and also for KZ2 sigma, which is same thing as applying B sigma to S sigma. So from there, we might hope to continue computing with the twisted bar spectral sequence, but this turns out to be quite difficult. On all of the ER pages, you end up having, so this is a small portion of the twisted bar spectral sequence, starting, well, that's computing, converging to the homology of B sigma, K sigma. And on each of the pages, you end up with portions that are not free, which are these various lines, and then you have different differentials between them. But you'd have to do a lot to actually compute all of these differentials. I have not verified all of them, just some of them. So, but there's other methods you can use in the C2 equivariant setting. Specifically, one can use a computational lemma due to Mark Behrens and Dylan Wilson. And what this lemma says is it.
Sorry, Sarah,
yes.
I had a question about the previous slide. So
yes.
just to summarize the strategy here, it's an inductive construction where you use the twisted bar spectral sequence to go from a known homology of some C2 equivariant Eilenberg-MacLane space in certain bi degrees, and then you can increment the sign representation grading by 1, right?
Exactly.
But you can still also increment the trivial representation grading by 1 using the usual bar spectral sequence. Is that how that works?
Yep, exactly.
Okay. And then by combining those two, you can iterate it to any bi degree you want.
Yes.
Okay, thanks.
Yep. It's just that often this twisted bar spectral sequence is not so well behaved, so it's a bit difficult to work with in practice. So then it's helpful to use this computational lemma, which says that if we have a C2 spectrum X and a set of elements in the homology of X such that on the underlying level, they form a basis for the underlying homology, and on taking geometric fixed points, they also form a basis for the geometric fixed points, the homology of the geometric fixed points, then the homology of the original spectrum X that we're interested in is free over the homology of a point, and moreover, the elements we started with form a basis. So a computational strategy is to start with the homology of K sigma, because we're able to compute that, we know what that is, and then use circle products to produce elements in the homology of KV, or where V here specifically is going to be some number of copies of the sign representation. And then use our explicit models for the star and circle product to analyze these two underlying and fixed points maps. And to analyze fixed points, it's useful to know what the fixed points of the spaces we're talking about are. And in the case of C2, the fixed points of some number of sign representations and trivial representations is going to be a product of non-equivariant Eilenberg-MacLane spaces. So for example, when we're looking at K sigma, which is twisted RP infinity, the fixed points will be K0 crossed with K1. So combining that computational strategy, you can verify that the homology of K and sigma, where n is any number, is exterior on circle products in classes that are in the homology of K sigma. So this answer does mirror the non-equivariant answer at the prime 2. And then from there, as Martin was pointing out earlier, we'd want to use the bar construction and the bar spectral sequence to then iterate to get to any other bi degree with some number of trivial representations. And to do that, it's useful to notice that an equivariant version of the Thomson-Wilson theorem does in fact hold, and that the circle product still does factor through the bar construction, and that the map on the associated graded pieces can once again be described inductively, which leads to an ROC2 graded bar spectral sequence pairing with one additional hypothesis, because ROC2 graded homology with coefficients in the constant Mackey functor F2 isn't guaranteed to be flat. You do need to have that like a flatness criterion, but as long as you have that, you still have the same sort of spectral sequence pairing that on the E1 page, once again, does have a very explicit form given in terms of circle products and iterated reduced coproducts, which are both things that can be computed very explicitly. So using this bar spectral sequence pairing, can write down the homology of K rho. So here, similar to the non-equivariant case, we're going to have some additional generators appearing. Here we'll name these beta bar i's, and these are coming from K0, which also does have a map to KF2 rho. And you can compute the E2 term, the TOR in this bar spectral sequence, and identify all the cycles on that E2 page in terms of circle products of elements in the homology of RP infinity, twisted RP infinity, and these beta bar i's.
And
then,
sorry, just remind me, the notation rho here is just a regular C2 representation, so trivial plus sign? Okay,
yes,
thanks.
Yep. And then we can iterate this as many times we want to get the homology of the sign representation plus any number of trivial representations. To write this down explicitly does require quite a bit of bookkeeping, so that's what's on the slide are simply indexing sets. And with those indexing sets, you can write down that the homology of the space is sign plus any number of trivial representations. It's going to consist of circle products of things in the non-equivariant homology of Eilenberg-MacLane spaces circled with something coming from the homology of K sigma and the homology of K rho. And then one would hope that you could write down something similarly explicit for all the remaining spaces, but this proves to not quite work in terms of the circle product structure. So if we're considering the homology of K2 sigma plus 1, most you can, so computing this from applying B to the homology of K2 sigma, and most of the cycles on the E2 page of the bar spectral sequence can be determined, identified using the bar spectral sequence pairing. So, in this first line on the slide, I have the space itself, then the underlying space to remind us that on the underlying, if we forget the C2 action, this is K3, and then the fixed points is K1 times K2 times K3. And most of the cycles on the E2 page can be identified in terms of circle products, which is what most of this bottom portion of the slide is. And the reason for the three columns is that on the fixed point level, this first column is giving us the homology of K1, the second column, the homology of K2, and the third, the homology of K3. And there are some elements, these by K, E sigma, circle E sigma, that cannot be identified in terms of circle products simply because they have too many sign representations in their degree. So this is something new on the E2 page. And so when we need to finish doing the spectral sequence computation in order to understand, is this a permanent cycle? Is there some more complicated differential going on? And it does turn out to be a permanent cycle. You can use Hopf ring structure in the bar spectral sequence, along with the fact that the co-products on the homology of K sigma, knowing that you don't really have any primitives, which in a Hopf, when you have a Hopf ring structure on an ER page of your coalgebra, then the differentials have to satisfy both the Leibniz and co-Leibniz rules. And in particular, this requires an algebra indecomposable to map to a coalgebra primitive, and there aren't enough of those. So in the end, that ends up implying that the DR differentials have to be 0. And so the bar spectral sequence does collapse on the E2 page, just with additional generators. So then in general, you can write the homology of the 2 sigma plus i's. Those end up being some non-equivariant parts of homology, circle product with generators coming from K rho, K1, K sigma, and then these new cycles that we're seeing up here. And then to write down explicitly the homology of other spaces requires greater bookkeeping that I don't have a good sense for. I expect, so even though I know the spectral sequences collapse on the E2 page, and one can write specific generators, it perhaps suggests that perhaps there's some other structure that would tie all of this information together in a neater package that would perhaps be nicer to write down explicitly, but at this point, I'm not exactly sure what that nicer package might be. So some future directions for this sort of computation in particular include that stably the dual Steenrod algebra has a relation. And one can ask, so from definition construction, the alpha parentheses i's should stabilize to the tau i's, and the beta parentheses i's to the xi i's, but it's not clear where an arbitrary element in the homology of KB should stabilize to in the dual Steenrod algebra, and it's also not clear how this stable relation arises from unstable information. So those would be some interesting questions to study. Additionally, it would be lovely to work out all of the differentials and algebra in the twisted bar spectral sequences, since we know what the E infinity page is. Perhaps that can be leveraged to really understand those at a deeper level. And then it would also be interesting to compute other analogues of equivariant analogues of Ravenel-Wilson computations, such as the homology of the spaces of the real Brown-Petersen spectrum. And then also studying other problems with ROC2 graded Hopf rings and how those relate to some other C2 equivariant spectra. And I think this point, that's everything I have to share, and I'll wrap up here.
All right, let's unmute ourselves, and thanks, Serre, for a great talk. Are there any questions or comments? You can unmute yourself.
Oh, okay, thanks. I had a question. So Beck, you were talking when you gave that Barons-Wilson theorem.
Yes.
Is that like a different Wilson?
Yes. Oh, right. Yes, I forgot to put the initials. Yes, this Barons-Wilson is Mark Barons and Dylan Wilson. The rest of the Wilsons are Steve Wilson.
So I don't quite understand. So the set of elements, so H star of X, but does that mean, is that something that's not the normal cohomology, right?
So this is the, it's perhaps a bit small to see, but this is the ROC2 graded homology.
Oh, I see.
Then,
okay.
Yes, so you need to produce some elements that live in the ROC2 graded homology and then check these two conditions.
So it has two different, the other ones are just normal homology.
Yes.
Oh, I see. And the different stars means a different thing. I see.
Yes.
So XE, that's just what is that? That's just the like the stabilizer of like the identity element or something. Is that what you mean by that?
But I mean, just forget the C2 action. So X was a C2 space, just forget it.
Okay, and then you have X. What does the other one mean? You said geometric fixed points. Like, so that's
Yes.
not homotopy fixed points then?
No, it's not homotopy fixed points, but since this talk is about spaces, the spectra I would be considering would be the suspension spectra of spaces, and geometric fixed points of the suspension spectrum is going to be the same thing as the suspension spectrum of the fixed points of that space. So
I see.
Yeah, so it has that.
So it just means the C2 fixed points.
Yep, exactly.
So are you interested? So I know most of the stuff you're looking at kind of like Eilenberg-MacLane spectra and other kinds of things like that. Are you interested in computing these things for spaces? There is, yeah, sorry.
Like what kinds of computing?
The reason I ask is because there's something called small covers, which are which are kind of combinatorially defined spaces with a Z2 action. Actually, they have a Z2 to the N action on them. They're kind of like analogs. There's these other things called like moment angle complexes or whatever, or like there's also like, it's kind of in this theory of like, toric. So let's say you take a toric, variety that's a manifold. So it has like a circle action, so it would have a Z2 action on it. Are you interested in those? But those things are kind of combinatorial defined. So they might be some, I don't know if you're interested in that kind of thing. It's kind of far away. It's in the other direction, maybe.
Well, I haven't thought in that direction yet, but it certainly sounds interesting to think about.
Yeah, okay, sure. Yeah, just because they're kind of like, they're spaces with natural S1 or Z mod 2 actions that are kind of defined combinatorially. So sometimes certain kinds of computations, you can compute with the combinatorics. That's the idea. So how is this related to equivariant cohomology?
So this is giving you the ROC2 graded homology of the Eilenberg-MacLane spaces, since this ROC2 graded homology is free. Dually, like you do know that the cohomology is like the actual dual of this answer. So it gives you the cohomology in that sense.
Or homology, I guess. It gives you equivariant homology or equivariant cohomology.
That what gives you equivariant homology?
So I think, Don, you're thinking of the Borel equivariant.
Yeah, right.
C2
Borel
cohomology.
Yeah. How is it related to that? Yeah, right. So if you just take, X cross G over EG, And
Right.
and then you take its homology. How is that related to this X with a 5-sided star? Maybe you said this at the beginning and I forgot. I don't know, but yeah. Right. That, and you can just take normal homology of that.
Yes. So for normal homology of this, so a reason to take ROG graded homology is that it gives a nice version of Poincare duality for manifolds. And a reason to motivate using this fancier grading is that in order to have nice duality results, you end up needing to be able to take these suspensions by representation spheres. And that, well, that leads to the flavors are rather different in that, like the ROC2 graded homology, but point is just this totally different sort of thing compared to taking ordinary homology of a space. Does that answer help?
I guess yeah, I mean, I was just wondering how those two things you wrote down, how H lower star of the Borel construction is related to this H other star. I was wondering about that.
So
the other reason
if we take the ROC2 graded homology of the Borel construction, I believe we don't get any additional information for that particular space. But in general, it's like a richer theory where you get these more complicated looking answers, but the ROC2 graded setting or ROG graded setting sees more structure than Borel.
The other comment I had was, yeah, so this kind of lemma here kind of looks like something that is something called equivariant formality. It kind of seems to me to have the flavor of that, which is that something is free over the cohomology of BG. So it just kind of has that flavor. That's why that's what it says here. H lower star X is free over H star. It seems to have the same kind of flavor somehow.
Okay. Yep. Yeah, I was just talking to someone the other day who was telling me about equivariant formality as well. So something that they'd like to read more of.
I have a related question about the different fixed points. Can you go to the slide? I think it's a little bit after that with a fixed point formula with a product. Yeah, that one.
Yes.
Right now we're all in spaces. Those are all just, you have some C2 spaces and you take fixed points. There are no spectra anymore on that slide, right?
Yep.
And I like the example. Let's think about the example. You're saying that if you take this by degree, just sigma and no trivial representation, you were saying that geometrically, I want to interpret that example geometrically. You were saying that geometrically, this case sigma is it's the twisted real projective space, right? Which I can think of as lines in a bunch of regular representations, infinitely many copies. And then we take the C2 fixed points, and is there a geometric interpretation of that equivalence? Because K0 there, in this case is K0 it's just a discrete C2, right?
Yeah.
And
So
K1 is just a plain old RP infinity.
Like K1 just joint union. K1
yeah, exactly.
Would be another way to write this. So it's like the fixed points is 2 copies.
Right. And what is going on geometrically?
So I think we can.
You're taking lines that are fixed by the C2 action, where somehow in half the coordinates you're using the sign and half you're not.
Right. So I guess we could think about lines through the regular representation. So here the C2 action is flipping vertically, I guess. Let's see. So I think that's not what I wanted to draw. So those might be.
So maybe naively, my hunch would be that, well, if you have lines that only go through the coordinates where you have the trivial C2 action, then those are all fixed no matter what.
Right.
And then if you look at lines, and that would be one of the two summands, and then if you look at some lines only going through the sign representation coordinates, and maybe they happen to be fixed by it, like they're, yeah, I want to think that there's somehow maybe vertical, well, maybe not vertical, but fixed
like,
by the sign. That's a silly example, but that would be the other summand. But maybe I'm being too naive in my hunch.
No,
So,
I think that is right, in terms of like how it, like, the fixed points are modeled.
yeah, is there? Yeah, there's got to be some geometry in the background.
Yeah,
Like,
yes, because like,
okay, great. Any other questions? If not, let's unmute ourselves and thanks, Serre, again.
Thank you very much.
Thanks a lot.
And thank you all for coming.
Thank
And
you.
you enjoy the rest of the week.